It's not the normal one. Okay, I got the recording started. So right now we're in chapter 6. Can you imagine? I know chapter 4, which is an introduction to some things. Now we're in chapter 6. Chapter 6 is really dealing with alkyl halides. And then we have this a second important class of reactions, which are called the nucleophilic substitutions. We'll talk about that a little bit later. However, we need to do a little bit of an introduction in chapter 6. So the first thing is that we want to be comfortable with an alkyl halide. All right. We just learned alk or alkanes and some reactions to those. And you guys are learning now that halogenation can happen. We talked about chlorination specifically, but we'll generalize that class as halogenations. We can add a halogen to an alkane, right? If I generate a free radical, strap the hydrogen, I can terminate and I can now make a carbon halogen bond. All right, and those class of compounds are known as alkyl halides. Very important is to recognize a difference between alkyl halides and vinyl and aryl halides. I don't have my laser pointer here, but if you look at the first structure of the alkyl halide, and that's the alkyl bromide, there's all carbon-carbon single bonds, and the carbon that has the bromine is involved with single bonds to everything else. So that's known as your alkyl halide. If I look at the vinyl halide, and we got vinyl chloride there, the carbon that has the chlorine is involved in what? A carbon-carbon double bond, right? All right. So that changes the name to a vinyl halide. And it's very important that we recognize that because it changes the chemistry, right? The chemistry is completely different when the halide is attached to a carbon that's involved in a double bond. And the same thing with your aryl halides, right? And the major aromatic compound that we're using in first semester is benzene. So all I did was replace one of the H's in benzene with an halogen. In this case here, I have an iodine. And this is an aryl halide. Again, the carbon that has the iodine is involved in what? A carbon-carbon double bond, all right? So it's very important that we recognize the difference in alkyl halides. I can have the vinyl or I can have that aryl halides. And look, if you look on the PowerPoint slide here, it does a great description of differentiating things by the hybridization. The alkyl halide has a carbon that's sp3 hybridized, but the vinyl and the aryl has a carbon that has the halide that's sp2 hybridized. All right, that's why we wanted to know the difference there because the chemistry would change. We'll talk more about that when we try looking at our nucleophilic substitutions. Okay, so typically alkyl halides are reactive because the carbon that has the halide is going to be extremely electron positive. All right, so what does that mean? There's a polar bond where the halogen has more of the electrons in that bond, so that carbon is going to have a delta plus, right? And you guys are going to learn here that that delta plus changes the name of the carbon to be something that's electrophilic. It's looking for electrons, right? So nucleophiles are looking for regions that are positively charged, okay? So I'm just want to remind you guys of that bond becomes reactive. Okay? Somebody says they're still waiting to get in. I'm not too sure what room they're in. And I can't, I'm on one screen. Give me one sec. What's going on with the room today? I'm just going to call everyone I can.
Dr. Cooper, while you're doing that, where can I find these PowerPoint slides?
Everything should be in Canvas. I'll go to
Is
Canvas.
it, are we in chapter
Chapter
5?
6 right now.
6? Okay. Thank you.
Huh? If you go to Canvas and Files, this should be the publisher PowerPoint slides. And right now we're in chapter 6. Okay, good. All right, so we know that there's a polar bond. We know the reactivity is going to be where the carbon gains electrons, and typically we break the bond with the chlorine would gain those electrons as well. Right, so we'll talk a little bit about that. Nomenclature, we talked about these, so I'm not going to try to overdo this, but if you look at the first example here, I got 4 carbons in a row here. On carbon 2, there's a chloro. We know the substituent name for chlorine should be chloro, so this is 2-chlorobutane. If I look at my example on the right, my parent chain has a total of 7. So up top, I have this CH2 fluoro group, right? All right, that substituent will be known as a complex substituent, right? There's a fluorine involved. It's not your typical substituent. All right, so we need to name that as a complex substituent. Conveniently, the first carbon attached to the parent chain has to be given the 1. So that puts the fluoro on carbon 2 there. And the parent chain for the complex substituent will be an alpha group. So in parentheses, we would say 2-fluoroethyl. So the full name for this molecule is 4 parentheses 2-fluoroethyl close parentheses heptane. Right? And for the most part, we should be pretty comfortable with naming alkyl halides, right? And there's a couple of examples in Pearson. In the homework, we'll also have some examples if you guys want to work on that. We'll look at this example here. There's 9 carbons in a row. On carbons 2 and 6 are where our substituents are located. Alphabetically ordered, though, bromo comes before the methyl. So we have to say 6-bromo, 2-methyl, non-name. I'll look at this ring here, right? We talked about this somewhat. All right, I got a potential tie. I can say 1 fluoro or 3 bromo, or I can say 1 bromo or 3 fluoro. Which is the correct way? I have to give the lowest numbering to the carbon that has the highest priority. Which carbon would have the highest priority? The carbon with the bromo or the carbon with the fluoro? All right, hopefully everyone knows that the carbon with the bromo should get the lowest numbering, right? Why? Bromine has a higher atomic number than fluorine does. And so that means that that carbon that has the bromine will be the higher priority carbon. And that higher priority carbon should get the lowest numbering. So I should put 1 at the carbon that has bromine, and the carbon that has the fluorine will be 3. So I can say 1 bromo, 3 fluoro cyclohexane. All right, keep in mind that they gave us some stereochemistry here. All right, and I'm going to just be simple for the day and just work on the relationship. If the bromine and the fluorine are both on the wedge, what could I say here? What's the relationship between those 2 molecules? They are cis on the same side to each other. All right, so is everybody kind of comfortable with those namings? Yes, no?
So,
No, okay, what's the question you might have?
I actually was just able to see this. I, I don't know. It was like a loss of connection. I couldn't see anything. I was
Okay,
just, uh,
all right, that's cool. Is it better now?
yes, sir.
Okay, good, good, good. All right, I think these are straightforward. I think you guys are comfortable with this. There's not too many tricks here. Um, we've been already somewhat naming things that had halogens already, so I'm hoping that everyone is comfortable with this. All right, let's talk about some common names, all right, because they're going to come up, unfortunately, in this class, all right? So we don't have to necessarily name alkyl halides by identifying the parent chain and numbering the chain, dealing with constituents and all that. Sometimes we just get very lazy and just name things by the alkyl group, right? So if I see a specific alkyl group attached to a halogen, I can break the name down and just say that alkyl group and then the halide. So let's take a look at examples here. If I look at the alkyl groups, and that's all the carbons, the hydrocarbon base in this first structure, right? All those carbons looks like an isobutyl group. So I can simplify the name to say isobutyl or bromide, I'm so sorry. If I wanted to name this systematically, IUPAC, the correct way, what would be the name for this molecule? Would it be 1-bromo, 2-methylpropane? Can you guys see that? Carbon 1 will have the bromine. Carbon 2 has the methyl. There's a total of 3 carbons in the chain. So that'll be prop. So this will be 1-bromo, 2-methylpropane. That's the IUPAC name. But the common name is just isobutyl bromide. All right, be prepared. I could use either or to describe a molecule, right? And you guys will have to be familiar with what I'm doing or what I'm trying to refer to. All right.
Can you draw it out or something? Because I don't see how you're getting isobutyl bromide.
Okay. You should be able to convert between condensed and line angle structures. I don't have my pen with me. Give me 1 second, though. Give me 1 sec. Let me see what I can do. Dang, I left it in my office. All right, give me a sec. I'm going to try to see if I can bring up the other screen. But if you need to, try your best to convert that. You just have a CH2 group, and then those last 3 carbons are branched like an isopropyl group, right? So it gives you a total of 4. 4 carbons, so that's why it's an isobutyl system, right? Okay, I'll do this because of the time it's taking. I'll try to come back to this whenever I go to the live setup. All right, the next example is butyl bromide. Can you guys tell me the systematic name for that compound? If I had to ask you to give me the real name or the systematic IUPAC name, what would you call butyl bromide? Any takers?
I have a question.
Uh-huh.
So the bromine and the methyl group, they're attached to the same carbon, right?
That's right.
That would be carbon 1, right?
Say that one more time.
That would be carbon 1.
That's correct.
Okay.
All right, good. So the name of this compound in IUPAC would be 1-bromo, 1-methyl propane. Right? Okay. And the last constituent is known as a butyl bromide. If I had to ask you for IUPAC, what would you use for that name?
IUPAC of the last one,
Yes, correct. Yes, ma'am.
it would be 2-bromo, 2-methyl pro.
Yeah. Not but you would say propane?
Okay, what's the difference between propyl and propane? Like, what's the difference between the YL and the ANE?
Yeah. Okay.
Oh, because that's the parent functional group.
Yeah, one is a substituent name. Propyl is just saying it's hooked on to some parent chain. You're just naming a side chain. And propane is saying that that's the main chain. That's right. So this would be 2 bromo, 2 methyl, and it's a total of 3 carbons, propane. Very good.
Why is it 2 and not 1?
Yep, because you need to identify the longest chain here. And so the longest chain would start from one of those methyl groups. So you have to go 1, 2, 3. You couldn't start in the middle of that chain because it will be too short. If you put 1 with a carbon that had bromine, then you only has 1 other carbon attached to it, right? So that only be 2 carbons in the parent chain. You need to get 3. So starting at the end will allow you to get 3 carbons, which is a longer parent chain. Does that help?
No, not really.
Okay, I'll try to come back to this. I just got my second computer up. All right, let's just go right to it. Let me see if I can draw. All right, so can you guys see the screen? I just converted everything to the main computer here.
Yes.
All right. Let's work on that first question really quickly. But you guys had this molecule here. Someone said that why is it called all right, sorry for the way it looks right now. All right, so the question here is why is this called an isobutyl group? All right, if you had to convert this into a line angle structure, you would get this. All right, is everybody comfortable with that? Let's go ahead and just for our sakes here, let's go ahead and identify the longest chain. That should be 1, 2, 3 here. All right, so that's 1, 2, 3 there. This is my carbon 1 there. This is my carbon 2 there. And this is my carbon 3 right there, right? And this group right here looks like what substituent? Or which, yeah, what type of substituent would you call that?
An isopropyl group.
This is iso, not propyl, but it's isobutyl, right?
Oh, because it's 4.
Yeah, because it's a total of 4. That's right. I have that fishtail look, so I know it's iso something. Because there's 4 substituents here, that's isobutyl. All right, so does that answer that first question that came up?
Yes.
All right, why is that isobutyl? All right, somebody asked me also, why is this carbon 2 and not carbon 1? All right, so let's convert that into line angle structure. All right, that's going to look like looks like that, right? And if I want to get the longest chain here, it's going to be best if I start on one of the ends, right? So it gives me 1 there, 2 is going to be here. 3 will be right there, right? So again, we said that the IUPAC name for this one should be 1-bromo, 2-methyl propane. Comfortable with that? And the parent, the IUPAC for this compound should be 2-bromo. Oh, I did the wrong. Well, that's fine. 2-methyl. Okay, any questions with those namings? No questions? All right, before we start working on the mechanism, to the PowerPoint slide, let's do a few more here, and then we'll be ready to start some mechanisms. So I'm going to switch the screen back here to the iPad. All right, you guys can see the iPad, right?
Yes, sir.
Okay, good. So we just got comfortable with using the alkyl branch and just the halogens name to kind of come up with naming molecules. And these are common ways. And we want to be comfortable with that because sometimes we use that interchangeably with the IUPAC name. All right. Now, there's also another class of common names. All right. So we just learned that we're going to learn that if I have 2 H's on a carbon and X2, we typically call that a methylene halide. And okay, I'm sorry, I forgot that Mr. Harris is in class. Let me try to bring up these PowerPoint slides. Can you see from here? Yes. But I'll bring them up on here too in a few. I'm so sorry. All right, if I have CHX3, and again, X is any halogen, it's going to be commonly referred to as a hollow form, right? We'll talk about that here shortly. And if I have 4 halogens on a carbon, we go straight to inorganic naming, which you guys learn in general chemistry. So we say carbon tetrahalide, right? Here, so here's some names down here, all right? So CH2Cl2 is known as methylene chloride. CHCl3 is known as chloroform, all right? And the last down there, carbon CHCl4 is carbon tetrachloride. So please be familiar with the methylene halide naming, the halophore naming, and the carbon tetrahalide naming. All right, again, any halide is any group from carbon 17. You guys probably heard of chloroform because people use that, if they wanted to do some harm to someone and passing people out. So I read that sometimes in the paper that somebody got kidnapped and they use chloroform to wrap it in a napkin to cause that person to pass out. Chloroform is very volatile, so that typically, if you smell a lot of it, you'll probably just faint. Right. So keep a note here to be familiar with these. There might be a question on your upcoming test where I ask you to pick which compound is chloroform, which compound is methylene chloride, which compound is carbon tetrachloride, right? Or I can use any other halide example, right? I can ask for iodoform. I can ask for methylene bromide, and I can ask for carbon tetrafluoride. Make sure you
see your string.
are ready for that. Go ahead. What was that? I didn't hear that question.
I couldn't see your screen.
Okay. Can you see it now?
No.
No. Okay. I'm gonna stop and reshare. Give me 1 second. All right. What about now? Can you see the screen?
Yes, sir.
Okay. Good. All right. Let's move on to the next thing. We're almost there. All right, we want to start to also classify alkyl halides. I'll be using that word interchangeably this semester. Classification is another way to say your substitution pattern. All right, are you just a methyl halide? That means that the carbon has 3 H's. Are you a primary alkyl halide, a secondary halide, or a tertiary alkyl halide, right? That's very similar to primary, secondary, and tertiary carbons. The only difference is you have to have a what present? An halide. So the primary alkyl halide is a carbon that contains a halide that only has 1 carbon attached to it, right? A secondary alkyl halide is a carbon that has a halide that has 2 carbons attached to it. And a tertiary alkyl halide is a carbon that has a halide that has 3 carbons attached to it. Okay, indirectly, we can count again the number of hydrogens. A primary alkyl halide will have a carbon with a halide and 2 hydrogens. A secondary alkyl halide will have a carbon and a halide that has 1 hydrogen. And a tertiary alkyl halide will be a carbon that has a halide with no hydrogens. All right, so be prepared to identify primary, secondary, tertiary, as well as methyl halides. All right, again, the next slide is just revealing how these things look, and you can also count the number of hydrogens to help out if you need to. All right, dihalides are very important in this class. All right, we're going to start forming these as well. So whenever 2 halogens are attached to the same carbon, we call that a geminal dibromide or dihalide. Okay, I think about geminal as a word as a Gemini, right? The Gemini is the same person that has a split personality, right? All right, a vicinal dihalide are where both halogens are on neighboring carbons. So in my vicinity or my neighbor, right? So a vicinal dihalide has halogens on neighboring carbons. A geminal dihalide has both halogens on the same carbon, right? It's going to be very important to keep track of those differences. And I might be using these words to describe the products that are formed. I might say that this forms a geminal dihalide, or this reaction is going to, perform or prepare a vicinal dihalide. Or I might say that reaction chemistry only happens at vicinal dihalides and not geminal dihalides. Right? They both have very unique chemistries. All right, this will be our last slide. I'm not going to go through this. You guys can read this. But alkyl halides are very important in a lot of different industrial and household cleaners. Okay. Boiling point densities and all that kind of stuff is there. Rule 1 here, preparation of alkyl halides. They can be formed from these free radical halogenations or these allylic halogenations. And we're going to talk about the allylic ones a little bit later. All right, I'm going to share my screen again from the main computer, and let's start working on our free radical reactions. Okay, can you guys confirm? Can you see the main screen here?
Yes.
All right, I'm going to open a brand new window here. Let's go new.
Yes.
All right, good. We're working on free radical halogenations. All right, let's see if I can make this a little bit bigger here. All right, there's 3 steps to this mechanism. What are the 3 steps?
Initiation,
Initiate,
Good.
propagation,
termination.
All right, initiation has no rad in my reactants, but I'm generating a radical, right? Step 2 is what again?
Propagation. Radical to radical.
All right, I have a radical, and I'm also going to have a radical in the product. So I start with a radical reactant, and I end with a radical product. What's going on in my termination step?
Radical to no radical.
All right, I start with a radical, but I end with no radical, all right? Be ready to identify these steps, all right? So let's do a review before we start to work on some new problems here. All right, so last class we talked about this molecule here. Still not letting me see everything here. All right, and we read that with bromine. All right, keep in mind, for me to say light or energy, I'm going to say HE. All right, that's coming straight from physics. E is frequency here, right? Not velocity, right? So whenever I have H with its Planck's constants and I have a frequency, that's another way of saying energy, all right? And that's typically really describing light, all right? I'm not going to have a solvent yet for this, all right? So if I did this, there are two potential products I can form, right? I can form this product or this product here, right? Is everybody getting comfortable with me so far?
Why all the extra lines on the first one and the second one?
Why are there extra lines? Not
Like
two.
you went from 2 lines to 3 because you add the bromine,
Yep.
carbons.
The carbon stayed the same, so that's why I thought maybe the question was on. So let me let's work on that. The best way I probably can answer that is by keeping track of carbons, right? So that's good. When I'm doing a reaction, I want to make sure that I realize that I'm not losing carbons in free radical halogenations, right? But you do want to keep in mind that I am replacing a hydrogen that we don't have to draw with a what now? A bromine, right?
The second.
So when we do this reaction, a bromine has to be added to the carbon here, right? So in this case here, these are the carbons and these are the potential products. So last class we recognized that there are two identical carbons here. I'm going to call this A, right? Carbon 1 and carbon 3 are exactly the same. Is everybody comfortable with that so far? How do I know they're the same? They both contain 3 hydrogens and they're both attached to which carbon?
2.
Carbon 2. They're exactly the same. And carbon B here is just carbon 2. So my products come from either adding a bromine to our A type or adding a bromine to our B type, right? So this is how we know we got 2 potential products from this reaction. All right, which product is the major product and which one is the minor product? Anybody help me out?
A is major and B is minor.
Okay, it's the opposite. So the major is really B, right? And this will be the minor product here. All right, how did I know that B was a minor? That was a good try, but how do I know now? Can you tell me, how do you know that B was the major product.
Yeah.
Connectivity of bromine.
Say that one more time.
The connectivity of the bromine.
The connectivity of the bromine. Okay, give me some more information.
It's off the third carbon on the minor one, and for the major, it's off the second carbon.
Okay, maybe we can answer this question with a mechanism.
Because the carbon has more bonds now. It doesn't have as many lone pairs.
No. Let's work on the mechanism. Maybe working the mechanism will help. All right. So first step has to be my initiation step, right? So I'm gonna take my bromine, do a what to it? So when bromine sees light, I'm going to get a homolytic cleavage. You guys remember that word? What does that mean?
It means that they're both gonna each take one electron from the bond that's between them.
That's right. Good. I don't really have good half arrows. These are half arrows.
What that word is again?
Homolytic cleavage. Give me 1 sec and I'll write it out here. All right, so step one is just where bromine forms a radical through a homolytic cleavage. Dude, this computer is having a mind of its own right now. All right, I'm gonna try to put these in red because these are important. All right, you guys will have to draw these arrows soon. All right. So this is a homolytic cleavage. All right, and what happens when I do a homolytic cleavage?
They become separated.
Okay, good. You get 2 bromine radicals, right? Try to make these big enough so everyone can see. Okay, good. Any questions so far here on the first step? All right, my second step is going to be what? What was
You
that?
gotta go from a radical, other radical. So you take one of them and you do something with it.
Okay, good. So my step here is going to be I'm going to do a hydrogen extraction. I'm stuck on that word homolytic cleavage today. All right, so there's 2 potential H's that can form. This is how we're going to get our major product. I'm going to say that this is the A carbon. I think I had that in a purplish color. And then we're going to have to show the mechanism also for when we pull on the B side. So I'm going to pull the B hydrogen as well. I think I had it in green. All right, so hydrogen extraction involves 3 electrons here. So this electron is going to be only 1 electron in that bond. Let me have it going the other way. Okay. And the other electron in that bond is going to reside back on carbon. You know what? I'm going to, just for convenience, I'm going to move this way. It might be easier to see it this way. All right, give me 1 sec. I'm just going to be a little bit particular because I want to make sure that this makes sense when you guys have to do it. And I feel very particular. I feel like maybe I didn't show this correctly, and this is why students don't draw things right. So I'm trying to see if I can get this to work. It won't let me do what I need to right now. All right, that's a weird looking arrow. Okay. All right, let's talk about this. So I'm extracting the hydrogen, right? And we know in a chemical bond, there's 2 electrons. So one of the electrons in this bond with the H is going to bond with this bromine single electron. And the other electron in this bond just resides on carbon. So let's take a look at that really quickly. What happens when I do this? All right, I'm going to move this A here. Let's put A like this. So now I form this compound here. And now it puts a radical there plus HBr. Okay. Everybody getting somewhat comfortable with that? I could do the same thing for my B type. Where again, only 1 electron in the hydrogen. Yeah, that's going to be the best I can do right now. They're going to meet. And the other electron in that bond is going to reside on carbon. So I'll take these. So what happens when I do this? I'm now going to form something that looks like I thought I copied that.
The dot gonna be on the second carbon.
It's this compound. All right, so I'm going to call this one up top radical A, and this down here radical B. All right, and if I ask any question in class on tests and exams to why you get this product as the major, is always answered from the potential radicals that are formed. So let's talk about the radical up top. If I had to classify, here's that term here. If I had to classify the radical, what will you classify it as? All right, when I ask for classification, is it primary? Is it secondary? Is it tertiary? Is it methyl? And there's be some new terms that come up. Is it a allylic, vinyl, or aryl? We'll talk more about those other words later. But what type of classification will you say here?
Would that be secondary?
Is it secondary?
So this is a primary, all right? We're gonna work on that. Let's work on that. Let me see if they give me my box here. View. I don't see that box here. All right, I need to put, we'll just put primary. I can't put my degree symbol here. All right, so this is how we do this. First of all, you need to identify the carbon that has the radical. All right, so I'm gonna put a big arrow here if I can. This is the carbon that has a radical, right? Is everybody comfortable with that so far? How many carbons are attached to that carbon that has a radical? You will tell me how many.
Could you zoom out a little bit?
Okay, sure. All right, so the carbon at the end has the radical. How many carbons are attached to that carbon? You would say what?
One.
Just one.
Just one.
So that's why it's classified as a what type of radical?
Primary.
Primary radical, right? So because I can't put my degree somewhere here, I'll just have to write the word primary radical. All right, please be prepared to do that. That's going to be invaluable for this chapter. You have to recognize what type of radical you're dealing with. All right, on the bottom, again, how do I recognize or how do I classify it? I look at the carbon that has a radical. I'm hoping everybody's comfortable with the fact that it's this carbon. How many carbons are attached to it?
2.
So this radical will be classified as a what type of radical?
Secondary.
Yep, that's right. This is a secondary radical. All right, so now this is going to help me determine which product is going to be the major, right? The major product will always come from the major intermediate. And for this reaction, the intermediate is a radical. We taught last class, there's 4 reactant intermediates, right? Carbon-cation, radicals, carbanions, and carbenes, right? So every reaction that you guys have learned this semester will have one of those intermediates for carbon. The most stable one will always lead to the major product. So who's more stable out of the secondary or the primary radical? The secondary radical, all right?
Secondary.
So this is the more stable radical. That means that it should lead to the what product? The major product. All right, let's try to finish up this mechanism. I can't believe it took a whole page just to do this mechanism.
Wait, can you explain that again? Why that was more stable in the major one?
Yeah, it's more stable because of the amount of carbons attached. Carbons are electron releasing or electron donating atoms. So when I have more carbons around a radical, I stabilize it better due to the fact that I can release electrons to it. Right? Radicals are electron deficient. I need people around that can share electrons with me. A carbon doesn't mind sharing electrons with another carbon. So the more carbons around the radical, the better. That's why it's more stable. So the primary radical only has 1 carbon next, but the secondary radical has 2 carbons next. That's better. It's more stable. And because it's more stable, it will always lead to the major product. All right. And that just comes from the fact that reactivity is different here, right? It's easier to pull this radical or this hydrogen than that one because things are favorable here as an intermediate. This wants to form this versus that. Right? So the reaction is going to dominate in that way. It's going to always pull here than pull the H. Did I answer your question? Is that yes or no? Okay. I'm going to start from the secondary radical now, just out of convenience. But you can do the same for the All right. So the last step here has to be my what step?
Termination.
Termination step. And how do I terminate? Don't forget, I formed
You get
two
rid
of these.
of the radical.
Yep, that's right. Initially, I had two of these. I used one to attract the hydrogen, and the second one is going to do what? Quench the radical, or terminate the radical. I'm going to draw a single-headed arrow. It's going from there. From there. All right, these two radicals are going to meet. And they're going to form this compound here. And again, we said that this is the major product. Right, just to be thorough, let me go ahead and try this to draw this one as well. Copy. But we're also going to have this radical. It can terminate as well with bromine, and it will produce this radical here, and we call this the minor product. Take home point. Most stable radical leads to the major. You want to commit that to memory if needed. The major, the most stable radical will always lead to the major product. All right, I know I'm out of time. Let's just do one example before we move on. All right. The question is this. First of all, how many potential products possible? Question 2 is, draw only the major product. All right, how many potential products for this?
3.
Okay, good. There's 3 potential products. How do I know that? I got to identify the different carbon types. So that's A. Oh, did I say 3? Did you say 3? It's not 3. I'm so sorry. 3 is not right. Let's
Should
see
it be
what-
2?
Yeah, 2. It's 2 products.
Oh, 2.
4. Oh, damn.
Right? All of these are A's. Is everybody comfortable with that so far?
So what you saying? They the same?
Yep. They're all the same type. They're exactly identical. And the
So what
second,
connects?
say that one more time.
Oh, never mind.
Oh, you can ask your question. I didn't hear you. I'm
Oh,
sorry.
no, you good. You answered it.
Okay. Okay. And our second type is here, right? There's only 2 types of products, 2 potential products here. Right? Is everybody comfortable with that? I'm sorry. I really wanted to do a more difficult question, but that's what came to my mind. This is the first thing that came. So my only 2 potential products. And how do I do that? I need to identify can't spell all different carbons or eliminate identical. Okay, so you want to identify all different types of carbons and eliminate any identical carbons. A are all identical and B are all identical, right? A has a total of 3 hydrogens and is attached to this central carbon here that only has 1 hydrogen, right? And that's the same thing that can happen on the other side, right? Down here, 2 A's, 3 hydrogens, and attached to this carbon that has only a central H, right? So that's how I know that this has those potential, okay, number of hydrogens. All right, can I draw the major product? What's the major product from this? All right, these reactions are pretty, well, that's a good question. What's the reaction, Dr. Cooper? I didn't give you a reaction. All right, so let me draw it out. That's why everyone is silent. All right, we're gonna just take this and react it with a halogen. All right, I'm gonna use the favorite one, Br2, in the presence of light. All right, now light is very important here. Br2 can do other reactions without light. We're not there yet, but keep in mind for right now, we're gonna need light. All right, so that means that I'm gonna put a bromine either on carbon A or on carbon B. Where should it go?
Carbon
A.
B.
On where?
I think it's on B.
It should go on B. All right, to answer this question, all right, to solve draw or consider both potential radicals. Stable radical leads to the major product, right? I'm hoping that we're getting comfortable with that. All right, let me put this in a box because this is the answer here. All right, let's look at both radicals really quickly. Radical from A would look like this right here, right?
Yeah, just an extended.
Hey, go ahead. I thought I heard somebody. All right, so this is A. And the other one here is B. If I had to classify the differences between these, what would you say? A is what type of radical? Yep, primary. Again, I look at the carbon that has what? The radical, this carbon right here. And how many carbons are attached to it? Only that one. So that'll be primary, right? And B is what type of radical? That's right, it's gonna be secondary because there's a carbon there.
2 carbons here.
Yeah, that's right. So who's more stable out of these two? That's right. This is the secondary. more. All right, how do we feel about that so far?
That's cool. So that's basically what you did with the electron was basically show us how to draw it. Like what is that called? The actual drawing.
Oh, you mean when I push the arrows? That's the mechanism.
Oh, okay. Will we have to draw that?
Yeah, you would need to know the mechanism. That's right. All right, let's do one more before you go, because that was a little too easy. All right, same thing. Can you tell me how many potential products and which one is the major? All right, I'm not going to break it down like I did the last one because I'm out of time. I'm way over time. All right, and this is going to be just a chlorination reaction.
I'd say 3.
All right, somebody says there's 3 potential products. Anybody else? All right, I made a mistake actually up top too. I just realized that. This radical is not secondary. Anybody tell me what it really should be?
Tertiary.
All right, that's a tertiary radical. I'm so sorry. Got stuck in just listening. All right, this carbon has 2 up top and 1 down attached to it. That's a tertiary radical. Okay, how many potential products here? What was the answer I heard somebody said?
Take a bid on 3.
Okay, Simmons said 3, which is not too bad.
I figured it was 4.
It's really 4, and let's kind of talk about that if we can. Right, I think everybody's comfortable with the fact that these 2 A's are the same. Right, B will be here, C and D. Okay, now I did skip a carbon, and can you guys tell me why I skipped a carbon? Oh, see what happened. This guy added in. I feel good. All right, there's 1 carbon that doesn't have any what attached to it. All right, this carbon right here has no hydrogens. So can it be used in a free radical reaction? That's a no, right? This cannot be used in a free radical reaction. Why? We know the mechanism steps, right? In my initiation state, chlorine has to break into 2 chlorine radicals, homolytic cleavage. But my second step is that I have to extract a hydrogen, right? That's the mechanism step for propagation. If I have no hydrogen to extract, will I be able to brominate there, chlorinate there? No. Okay. The 4 initial carbons, however, that's not all that's correct here. There's an E. Where? Right there. Those carbons at the end can also potentially form a radical. So that gives me how many potential radicals for this reaction? Everybody still with me?
Yeah.
5 of them.
Okay, good. That's right.
So I figured it could have been 5, but I didn't know if we were gonna consider all those.
Okay, no, that's good. That's good. If you follow that, you are doing a really good job, actually. You're right where you need to be.
All right.
Very good. Very good. All right, can you guys help me classify these before we go? And I'm going to draw the major product, and that'll be it. So from the radical that can form from A, what is that called? What type of radical will that be?
Primary.
Okay, good. Give me one sec. Let me catch up with y'all. This takes a little extra work. The computer here. All right, I'm trying to make these as a set of notes, so I'm doing some extra stuff just so I can release these to you guys right after class. All right, so again, I look at the carbon that has a radical right here, and I realize there's only one carbon attached, right? Everybody is getting it right here. The radical from position A should be a primary radical. All right, what about from position B here? What type of radical is this?
Would it be turned?
Okay, I think that's right. All right, I'm starting to get happy now because I'm starting to really feel like I'm teaching now. You guys are really starting to get this. That's makes my life a lot easier. Good, good, very, very good. This is definitely tertiary. That's very good that you can see that. Okay, what about the next radical? I'm gonna have to make this a little bit smaller.
Primary.
Who said that? You don't have to be shy. I'm sorry, I pointed my arrow at the wrong position here. All right, I need to look at the carbon that has the radical. Is this carbon right here, right? And how many carbons are attached to it?
3.
One more time, take a real close look. If I look at that carbon and say who's attached to it, only that carbon right there, right? So it makes it only 1, and this has to be what type of radical?
Primary.
Yeah, primary radical E.
Hey, I sure was wondering what we consider here because of, by being branched out.
So we don't count. We don't count the the 2 on the side.
2 on the side. I'm not sure I'm seeing that. So we're looking at this carbon right here, right? How many carbons are attached to it? Only this one. Now this one has this carbon and that carbon attached to it.
Oh, okay.
Not that carbon, right? Okay, good. That is a primary radical. What about the one that came from, what is that, C here?
That'll be secondary.
Very good. So again, I'm looking at this carbon only. And when I look at that carbon, I realize there's only that carbon and that carbon attached. So that makes this a secondary radical. And the last one at the end.
Primary.
That's right, it's gonna be primary. This came from C. Secondary. And I'm gonna put my arrow and that only has one carbon attached to it.
Dr. Cooper,
Go ahead.
looking at what we just wrote, does that mean B is the most stable
Yeah, that's correct.
and the major product?
It's gonna lead to the major product. Yes, ma'am.
All right.
Wait, which one is that?
The more stable radical here.
Oh, B. Yeah, tertiary.
All right. So I know that my
B,
tertiary
B and D,
radicals
or just B?
at position B is gonna lead to my major product.
Oh, at position, I got you, because it's more stable because what's associated with it. I got you.
Yeah, because of the radical that forms there. Right.
Got you. Okay.
So if I had to draw my major product, this would be the major product.
Dr. Cooper,
Yes, ma'am.
why you put tertiary for the last one?
Oh, it's a mistake. I'm sorry. I didn't mean to. I'm so sorry. Thank you. I think I put tertiary because somebody asked me what is the tertiary part of the major one. I'm sorry.
Confuse me.
All right. So if I had to look at this reaction of this compound, there's 5 potential products. These are the potential reactant intermediates, or radicals. And B, because it's tertiary, would be the stable radical, and it will lead to the major product. So I will replace the H there with a chlorine. All right. Any questions so far?
No, that was pretty good. Pretty good.
Okay.
Dr. Cooper,
Huh?
how much longer are you going to be? Because I have to log out soon.
You could go. I have the recording, so if you need to go, you're always welcome to leave.
Okay. Did you take attendance already?
Attendance comes from Canvas, not from Canvas, from Teams. So it automatically marks people that come in and out of the room.
Okay.
So I don't do attendance. I just get the log that Teams give me. I just have to load that after class.
Okay. I'm gonna log out in 7 more minutes.
Okay, that's fine. I completely understand. This is the last problem that I want to do.
Okay.
All right, 5 potential products here. The major product puts our groups, or puts a bromine on position B, right? Because it's from the tertiary radical. All right, good. So this is our general class of halogenation reactions. It looks like you guys are getting it down. We're gonna, I probably will have a quiz coming up soon on this. Also keep in mind that chapter 6 deals a little bit with these same reactions, but then it starts to move into some other potential reactions that can happen once we form that alive, right? So we'll talk more about that on Monday. What happens when I do a halogenation and form this compound? This compound now is reactive. We start to talk about that. All right, before we leave, can you guys name this molecule? What's the name of that molecule? What's the parent chain? How many carbons in the parent chain?
5.
Yep, 5 is the parent chain. Good. I got sustentions on carbon 2, and I got sustentions on carbon 3, right? Hopefully you are numbering that chain correctly.
See, that'd be the hard part, like putting everything in like order and how to translate what it actually is.
Okay.
2I, so you're saying on number 2 carbon, you got the chlorine or chloride. So what? Carbon.
Yep, so let me
see. Yeah, that'd be confusing me, dog. I'd be like, what?
All right, so carbon 2 is a carbon that has a chlorine. It also has a methyl, and carbon 3 has these 2 methyls here. So it's 1, 2, 3, 4, 5. So it's 2-chloral, 2,3,3 trimethyl-pentane. All right, you guys are okay for now, but keep in mind, we want to use all the skills for chapters 4 and 6. All right, I'll see you guys on Monday. I'm going to stop the recording, and if you have a question, you're more welcome to ask.